All right, so when we're looking at water, we want to have an understanding of exactly the processes that water undergoes, so the hydrologic cycle, the water cycle. It's going to be driven by sunlight, and essentially what we'll see is as water evaporates, it's then going to ultimately wind up just then condensing in precipitation, so either rain or snow. That's then going to run off into lakes and rivers again, and we'll kind of just see that process occur again. We also have some other processes, so transpiration similar to evaporation. It's just in this case sort of leaving the plants rather than soil or the oceans or rivers, whatever it may be. And then one thing that often gets overlooked is just groundwater. So things like oceans and rivers and lakes, those are known as surface waters just because they're on the top of the Earth's surface. But we've also got groundwater, which is just water that's located in the soil below the level of the surface. And the water in the groundwater can actually flow. So in this case, it's just showing groundwater flowing from the lake into this ocean. But with the water cycle, like I said, it's going to be dependent on solar energy. And then because of that, we're going to have an uneven distribution of water. It's also going to be impacted by just the general landscape of whatever that area may be. So mountain ranges, for example, often have one side that typically gets much more precipitation than the other. So in addition to just the weather itself, the landscape can impact the distribution of water. And then with this distribution of water, with this cycle in general, global warming and climate change does have the ability, does have the potential to alter that cycle, to alter that distribution of water. And if we think about it as the water, or as the temperature continues to rise as global warming continues to occur, we're just going to see more of the glaciers, more of that snow melt, just melt, and we're not going to get any of it sort of reforming. So generally in the winters, we get more of the snow and the glaciers reforming. We're just going to see less of that process occur until we're ultimately just having less and less of that snow, less and less of those glaciers present. And then we'll talk about that a little bit later on, but that's going to have a big impact on specifically like drinking water and water use for human consumption, just whatever that may entail. And then with the distribution of water, we can also think of it in terms of the different compartments. So sort of where is it located, or what type of body of water is it located? And we can see most of the water on Earth is going to be located in the oceans, almost 98% of it. The vast majority of the remaining water is going to be located in ice and snow. And then we've just got a small amount in these other compartments here. And then we can also just see the residence time, so the amount of time we expect a water to stay in that compartment. So with oceans, very long time. Ice and snow, depending on where it is, could just be a very short period of time to a very, very long one. But again, most of the water on Earth is going to be located in the oceans, which just means most of it is going to be salt water. So it's not going to be something that humans, at least in the natural form, would be something that humans are going to be able to consume. And where water is located has a very big impact on where humans ultimately decide to live. If you noticed in the history and social studies classes that you may have taken, most of the civilizations that you study are probably located near some sort of port, some sort of river, so that they have the ability to import and export goods, but also so that they have the water as a resource for drinking, for watering crops, for cleaning, for whatever they may need it for. But that also can lead to conflicts. You may hear the term water wars. That could potentially be something that comes into play in the future as the water supply dwindles, especially in certain locations. But one thing that could hopefully sort of counteract that is innovation. So desalination techniques allow for salt water to be converted into fresh water. So hopefully in the future, in addition to conserving water, using it more intelligently and things like that, hopefully we also come up with different techniques that allow for things like salt water to be used more readily. And then with this water usage, you can see on the right-hand side, depending on where you live, depending on what country you're from, there's going to be a difference in the average water usage. Some of that may be due to just the availability of it. Some of it may be due to differences in lifestyle, from dietary choices to agricultural usage. But the lifestyle itself is going to play a big role in exactly why we see pretty large differences in the average usage from a person in America versus a person in Mali. And part of that usage is going to come down to the dietary choices that people make. So different foods are going to have different requirements in terms of the amount of water they need in order to be produced. So with plants, different plants need different amounts of water. So you can see that here with just some of the different examples. But in addition to plants, we've also got different types of meat, because we've got to provide water for whatever that animal might be. So pig, cow, whatever. And that's why you can see at the top here, cheese is going to be an extremely water dependent food, just because it's going to come from cows, which are going to require a whole bunch of water. And then the milk as well is going to require water. So it's just going to be a very water intensive process. And we can see just some of the other choices here. So with this, in terms of trying to think with an environmental sort of lens, the dietary choices you make can have pretty big impacts in terms of the amount of water that is needed to provide or produce those foods. And then in addition to this, what you also want to consider if you're trying to think about how you can sort of minimize your environmental impact is where these foods are coming from. So even if something uses less water, if we're then obtaining that food from a very, very far distance away, we're going to have to ship it there. That's going to use fossil fuels most likely. So there's going to be other considerations. So that's one of the reasons why people often say like shop local or support local farms, things like that. Because in that case, you don't have to worry about the transportation. And then if you're choosing some of these less water intensive items, you can really minimize your environmental footprint that way too. And then in terms of the usage, though, the main usage of water is going to come from industry. So we're going to see power plants require a large amount of water, and this is used for cooling. So they essentially pump the water through the different parts of their power plant, because the colder water helps to keep the system itself at a reasonable temperature, keeps it from overheating. If it overheats, there are the potential for like different types of shutdowns, depending on exactly what type of power plant it is. The irrigation here, that's thinking in terms of agriculture. So watering the different crops, providing water, in some cases could be providing water for livestock, things like that. And then we've got smaller percentages for just like household usage, public supplies of drinking water, and things of that nature. But again, the biggest power plants and just agriculture. And another use related to industry is going to be fracking or hydraulic fracturing. And the way this process works is they essentially take a drill deep down into the earth, and then they eventually have that drill kind of go perpendicular almost And then there's a little bit more going on, but they get these fractures, these cracks in the earth. And then what they do is they pump a whole bunch of water along with some other chemicals in here. And then the pressure from that ultimately allows or kind of forces out the natural gas, which then just flows out of the well and then can be collected. So there's issues with that in terms of some of the gas can actually escape, and then we're having methane just released into the environment, which can contribute to global warming. But if you look at this process, what can also occur is there can be leaks. And then if you look, this is going to be a water aquifer. So in some cases, this may be groundwater that's used for drinking water or some other purpose. And if there is some sort of leak, now the water that they shot down this well, which also has different chemicals kind of mixed in it to make the fracking work better, now that's going to get into the drinking water, and it's going to be extremely, extremely difficult to clean. So fracking can help provide natural gas, which is a slightly cleaner alternative to more traditional fossil fuels like coal. But it can have pretty big natural or pretty big consequences on the natural environment, including with the water. And then with all of that usage, one thing that we have to consider is if that usage is going to eventually lead us to a place where we no longer have a viable amount of water. And in certain cases, in certain locations, that situation is approaching more quickly. So you can see those locations in the darker red colors. They're using a much larger percentage of the water that they have available. The lighter colored countries, not as dire, but this is going to become a more problematic situation just everywhere as global warming increases, just because that's going to decrease the amount of water that we have available. And then as that water decreases, as we're thinking about surface water in particular, so as lakes and rivers, things like that, as they start to dry up, as that water starts to evaporate away due to the increased usage or the increased temperature just leading to more evaporation, what people often do is they drill into the groundwater, they dig deeper wells, and they use the groundwater as the new source of water. This is a very short-sighted strategy, and you can kind of see on the right-hand side here. This picture is also in the textbook. You can see kind of why this isn't going to be a good long-term idea, because as we drill into as we drill the wells into that groundwater is going to be extremely, extremely slow to replenish. So as we kind of use it up, it's going to take a really, really long time for that supply to replenish, to get back to the original levels. So what can actually happen is the water gets removed, gets used up, and then before new water can kind of come in and refill it, those air pockets, because now that there's no water there, there's air pockets, those air pockets can kind of collapse, and we actually see what's known as subsidence. So we actually see the soil level start to sink, because as those air pockets fill in, the soil just starts to settle a little bit more. So we start to see it decrease. And that's what you're seeing here. So this occurred in the San Joaquin Valley in California. You can see in 1925, way up here on the telephone pole, that's where the level of the soil was. But then as they started to deplete that groundwater, subsidence started to occur. So that soil level started to sink and sink and sink. Over 30 years, we dropped this far. And then over the next 22, it went even further. And again, that's just because they started digging wells into the groundwater, started using up that groundwater. So the soil kind of started filling in those cracks and just started sinking down. And then another usage of water is going to be in dams And then dams are just used for a couple of different reasons. So sometimes it's used for providing energy. Sometimes it's used for a water supply for drinking water or whatever it may be. And for those reasons, they're highly advantageous. So they do have purposes. Otherwise, we wouldn't do them, wouldn't make dams. You can see a couple of the other ones at the bottom. So help with flood controls. Like I said, reservoirs for drinking water. In some cases, they could also be for recreation. Power generation, probably the biggest one, because it is a relatively, not relatively, it is a clean energy. But with dams, there are disadvantages, and sometimes these get somewhat overlooked, but they include just the environmental impact. They're going to force people off their land, and oftentimes this affects minorities and lower income groups more often. There's some evidence to suggest that dams can also be involved in, or can help lead to, earthquake activity. And then also when we make a dam, you're effectively sort of cutting off the water at that point. So now anybody downstream of that is no longer going to receive those resources, or at least not to the extent that they had been. So if we now build a dam somewhere, and this is particularly problematic in different countries where they're no longer working together, because at least in like with different states in America, at least we're somewhat connected. With the federal government, obviously the different states can do their own thing to some degree, but we're still somewhat connected. Whereas now when we think about if this was occurring between two different countries, now there may not be any sort of relationship or working relationship between the two. They may not be planning for one another. So if one builds a dam and they're upstream of the other, now they're effectively cutting off the resources, which could be dire for the people of that downstream region. And then with this, one of the written assignments is going to be focused specifically on the Snake River dams. So they're located in the Pacific Northwest here. They help provide energy, help ship goods, but they also negatively impact the environment to some degree, like we mentioned. So it's going to be up to you to kind of research that a little bit, get some more details about that specific case. And then just kind of decide for yourself if you think the Snake River dams should be left as they are, continued using them, or if they should be removed. And then with the water supply, we're focused again mostly on the usage of it. And to use it, we want it to be clean. One way we can kind of help keep the water supply clean is by supporting our forests. So one of the earlier directors of the National Park Service was a big proponent of the forests and keeping them clean, because this helps protect the water supply, and water is going to be arguably the most valuable resource we have. But the reason that protecting our forests help keep the water clean is for a couple different reasons. So if we look down here, forests filter pollution out of water. So the roots themselves, and then sometimes the plants can actually absorb some of those pollutants. So they actually essentially filter out the water. And they can do that to some degree with the sediment as well. But in addition to that, the forests, the roots help maintain the soil, so they help prevent erosion. And if we have a lot of erosion, now we're going to have the soil continuously flowing into the water. So we're just going to have just a lot of stuff, a lot of suspended material in that water. It's not going to be clean in that sense. And then that could also bring in other materials. So in addition to that soil, that could bring in other contaminants with it. So having that strong forest to kind of keep that soil rooted down is going to help keep the water clean. And then the final point is just the forests themselves kind of help. We've talked about it a little bit with the rainforest specifically, but they help keep the water supply and help keep that water cycle working as it should. With this, we would still need some sort of treatment option, so we wouldn't just want to take the water exactly as it is and drink it, but it would help keep it cleaner, help reduce the cost of actually that final filtration that we do ourselves. And with water, what we're looking at here is what's wastewater and actually recycling it. So this wouldn't be something, at least at this point, something that would be used for human consumption directly, but it could be something that is ultimately used for agriculture, so watering plants. But you can see that they're taking the wastewater, and then just through successive steps of cleaning, it's getting more and more purified, ultimately to a point where it does look pretty clean. Again, it's not to a level where it would be acceptable for a drinking municipal drinking system most of the time, but it is clean enough that it can be used for other purposes. So again, like watering crops and things like that. When we're thinking about the water and the quality of it, one thing that's often used to sort of gauge that quality is the level of dissolved oxygen. This is going to be important in terms of the amount of organisms that can survive in the water itself. And the way oxygen gets into the water is just through essentially mixing with the atmosphere. So we've got oxygen in the air, it's just going to mix in with the water itself. And then in addition to that, when these plants, the algae and things like that, produce or perform photosynthesis, they're going to produce oxygen then as well. But we do have fish and other things living in here. We do have bacteria, and the algae are going to perform respiration, so it's going to use up some of that oxygen as well. And we've got a term known as biochemical oxygen demand, so BOD. This is sometimes also often used as a measure of the water quality. And what it is just a measure of how much oxygen is used by microorganisms to break down organic material in that water. So this organic material is just ultimately going to get broken down by microorganisms, and that process itself is going to use up oxygen, and that's what we're looking at with the BOD. So the higher the BOD, just the poorer the quality of that water is going to be, just because we're going to see the oxygen levels get depleted more and more because those microorganisms are going to be using it up. And then in another sense, we can see oxygen get depleted in water systems through eutrophication. So this can occur from just excessive nutrients in the water. The most common example is just with fertilizers. So we're going to have nitrogen and phosphorus in those fertilizers. Rain can come down and just have the rain essentially wash it off into the water supply. And that's going to support an algae bloom. And then the algae is going to block the sunlight. The algae is going to use up the oxygen. And then since it's blocking off the sunlight, we're not going to have any other photosynthesis occurring down here. So we're going to ultimately see the oxygen levels plummet. We're ultimately going to see fish suffocate, and just the amount of life that can live in the whatever this body of water is, just really see it plummet. So that's one of the reasons fertilizers, or excessive use of fertilizer at least, is problematic, because it can lead to this eutrophication process. And when we're thinking about pollutants, one type of pollutant is just going to be pathogen. So anything that causes or an organism that causes a disease. And these are responsible for 25 million deaths per year, mostly in children in poor countries that don't have a safe ways to dispose of sewage. So they wind up getting the sewage mixed in with the water. And that's how they get the pathogen introduced into their system. And with this, I actually worked at the water department back home in New York one summer. And with this, it's really expensive and time consuming to test for everything. So what they do is they generally just test for coliform bacteria, because that covers a couple of different things. And then if they wind up seeing that being present, they usually just use that as an indicator that the water quality is just unacceptable for drinking, or unsafe for drinking at least. You could boil it in a lot of cases. That'll be fine as long as you boil it for long enough. But at least just drinking it, without that, we wouldn't want to do it. And then another class of pollutants is just going to be the heavy metals. So we've talked about these quite a bit with combustion of fossil fuels, the leaking from mines, especially after they're not closed properly, but other processes can release these, including natural ones. So things like volcanic eruptions can release metals into the atmosphere. They can ultimately make their way into the different bodies of water. And with these, we're thinking particularly about metal and lead. Going to be two big ones, going to be able to bioaccumulate, as will cadmium and nickel, but mostly you hear about mercury and lead. Those are going to be two big ones because those will attack the nervous system and also affect the cognitive abilities of the person being exposed. But with these, what I want to point out just down here, there is ways to remove these heavy metals from our drinking water. So they're showing one example where they're just using some sort of graphene substance to essentially looks like absorb them. But then there's also, if you look, we've got positive charges here. So in some cases, they can use the ions to remove them. And in some cases, they actually use the size of those particles themselves. So there is a way to remove these substances from water. But like everything, it's always more expensive to do it afterwards. So if we can, we always want to try to protect the water supply. Just like we talked about in the last chapter, we want to try to protect the atmosphere rather than clean it up afterwards. We would want to try to protect the water supply rather than clean it up afterwards as well. And then in addition to the metals, what we'll see is arsenic and selenium are going to be similar. So highly, highly toxic. This is particularly a big issue with the groundwater wells in India. They tend to have high concentrations of those two elements. But one thing that also affects the water quality that may not seem like as big of a concept or big of a problem, I guess, is sodium chloride and the elevated salinity levels. So if we just have more salt in those waters, are going to negatively impact the ecosystems. Organisms can only survive in certain levels of salinity. So if it gets too high or too low, they're just not going to be able to ultimately survive there. So with this one, it comes into play in the winters when we're salting the roads to make sure that they don't ice over. But that salt is ultimately going to get washed off the roads, ultimately going to make its way into different bodies of water, and we'll see the salinity increase. So that's going to be something else that we have to kind of consider when we're trying to balance environmental protection and then sort of human ease and the lifestyles that we choose. Because obviously we're going to have people driving around. We need people to be safe. But if it's going to be a negative impact on the environment, we have to kind of figure out how to balance those two interests. And then with the organic chemicals, again, we talked about these when we were looking at the atmosphere. So these comes from pesticides, huge source of these types of chemicals, plastics as well. Pharmaceuticals. So these pharmaceuticals can actually make their way into the water supply because people take whatever those medicines may be. And then in some cases, they just get excreted through their urine, get into the water, ultimately just through that whole process, get into the environment through the water system that way. And in certain cases, we can actually see the pharmaceuticals get to measurable concentrations. And in some cases with xenoestrogens, they can actually cause disruptions in certain systems within the whatever that organism may be. And a lot of this stuff we've talked about before. But like the pesticides, we're seeing those run off from the agriculture environment, or in some cases, they're getting transported through the atmosphere and then depositing into the water. But we'll also see chemicals actually leaking out from landfills. So we dispose of things in one location, but then they're still going to sort of seep out from that location. And they can get into particularly with the groundwater. When we're thinking about landfills, that's going to be an issue. And then with this water supply or water pollution, we didn't have signs like this back in New York exactly, but because the Hudson River was polluted with polychlorinated biphenyls, so PCBs, those could bioaccumulate, they could build up in the fish. So the fish in the Hudson, not something that you would, Hudson River, not something you would generally want to consume. And you can see signs like this in a lot of different locations where there may be some sort of contaminant, again, particularly mercury and lead, but there's a bunch of other things. So with the fish, you've got to be careful about where you're getting that from. And there are recommendations on what type of fish you should eat at different intervals. So there's some fish that you can eat pretty much regularly. There's other types of fish that you may not want to eat more than once or twice a month, just because you may be exposing yourself to more of those chemicals that have the ability to bioaccumulate. And then with this, the microplastics, there is going to be a video in the chapter module focused specifically on microplastics, but with these, they come from a whole bunch of different sources. But they're essentially just plastics that are getting weathered down and eroded into very, very fine pieces, very, very small pieces. And these are present in huge quantities throughout the environment, including the oceans. They're also in the atmosphere. They're also in the human body. So unfortunately, microplastics are actually almost certainly in your blood at this point. Just because plastics are so ubiquitous, they're used everywhere. And they've been used for quite a long time now. So with these, I'm not going to go too much into the microplastics, just because there is going to be that other video that will dive specifically into these, but you can see just the different sources. So synthetic textiles, car tires, city dust, road markings, marine coatings, personal care, and plastic pellets. And then PFAS, so per and polyfluorinated alkyl substances, is just what PFAS stands for. These ones, this I've actually sent out the video for John Oliver a couple times, or at least posted it in a couple different places because it's kind of been relevant. So if you want to learn specifically about that, that may be, or about this, that may be a good video to kind of go into. But these per and polyfluorinated alkyl substances, again, that's what PFAS stands for. They're essentially just substances that have long carbon chains, and then they've got a bunch of fluorines on them. Those structures make them very useful in terms of these different products. So water resistant clothing, non-stick cookware, two of the big ones, but they're using a whole bunch of different things. But because of that, they're also highly persistent. So they just stick around in the environment for a very long time. They can also build up in the, they can bioaccumulate. And then these as well are going to be pretty much everywhere throughout the environment. And then they're pretty much almost guaranteed to be in your blood too. But yeah, with these, again, another video located. This one is not required, but there is a good video on PFAS, and it is pretty interesting, I think. So I think I'd recommend watching that one. And with the water supply, what we want to think about is the concentrations in water. Ideally would be 0. So ideally we would just have water. But if you think about water, that's going to be something that you consume regularly, something that you consume in fairly large amounts. So even if the contaminant is at a fairly low level, it's going to be something that we're constantly exposed to. So that's why with the water supply, particularly when we're thinking about drinking water, that's going to be why we need very rigorous standards in order to protect human health. Because even if we've got like relatively low thresholds for what we're considering acceptable in terms of these contaminants, we're going to be drinking this for multiple cups a day. So it's going to be something that we've got to make sure that we're protecting ourselves with. And that said, bottled water is generally going to be less safe. So some people think that it is going to be cleaner than what you get from the tap. And in some locations, if you're in places that have just particularly poor water quality, so like Flint, Michigan, that's a whole situation because they switched they tried to save money. The government did try to save money. So they switched from I think it was the Detroit River to the Flint River in terms of what they were using for the supply of their water. But the Flint River was much more corrosive. So it wound up damaging their pipes, wound up introducing lead into the water. And I believe it's still not dealt with for some reason. I don't know how that's possible. In that case, bottled water would almost certainly be a healthier alternative. But in general, bottled water is not going to be as clean as what you can get from the tap. And the reason for that is going to be a couple different ones. One is because the plastic themselves from the bottles can actually have chemicals sort of leak into them. So particularly the longer that bottle is, particularly the longer the water is just in that bottle, the more of those chemicals will have seep in, but also how it's stored. So the higher the temperature that water is in, more of those chemicals are going to sort of leach out of the bottle into the water. That'll contaminate it to some degree. But also municipal drinking water is tested much more frequently and it's held to higher standards than bottled water is. And also bottled water sometimes is kind of just recycled tap water. So whatever you're paying for is just the same thing you could get out of the tap in some cases. But also just the process of making the plastic uses more water than it can actually hold in the bottle itself. So it's not going to be an environmentally friendly practice in that sense. But the plastic here can take an extremely long time to biodegrade. It is relatively easy to recycle, but the vast majority of water bottles wind up in landfills rather than being recycled. So we're just creating a large amount of waste. It's not cheaper. It's worse for the environment, and it's also worse for your health in almost every case. So generally, you should be drinking tap water instead. And then with the water quality in general, just the issues it faces in terms of keeping it clean or cleaning it if it is contaminated is similar to the air quality in the sense that when we do focus on it, we do see improvements, and it is something that we can manage and something that we can sort of protect as a resource and use properly. But some of the issues that make it difficult is that a lot of the pollution that affects the water, similar to the pollution that affects the atmosphere, isn't going to come from just one specific location. So in some cases, it may just be a giant pipe that's leaking or dumping out a bunch of waste into the water. In that case, it's pretty easy to kind of just identify that as the source of the waste, cut it off, and then you can more or less have that just cleaned up. But a lot of the times we'll see what are known as non-point sources. So it's not going to be as easy to identify. It's not going to be as easy to just control and shut off. And that's going to be stuff that's like runoff from agriculture. Your textbook also mentions the case of pet waste in New York City that winds up running off into the water. But fossil fuel combustion, we've talked about the pollutants that come from that. They're ultimately going to wind up in the water as well. And then just the atmospheric transport that we talked about with the air pollution. So these chemicals have the ability to move, but eventually they're going to find somewhere where they'll just deposit. But when that occurs, it's not going to be depositing where it was sort of produced. So it's going to be tough to kind of cut that off. And then with this, like most of the environmental issues, water quality is going to more impact the poorer communities, just because they won't have the resources or as much resources to purify it, to build a water system, whatever it may be. And then typically also the poorer communities are going to be located closer to waste sites, so they'll be more located, or they'll be closer to the pollutants in general, and they'll have less resources to deal with those pollutants. So it's kind of a double whammy in that sense. And then with the groundwater, talked about it a little bit with the fracking, but with this groundwater contamination can come from various different places, like the landfill, so it can seep out and get into the groundwater that way. In some cases, and this is actually a pretty large source, septic tanks can do something similar. So they'll have the leaks ultimately wind up in the groundwater. And then, just as we've talked about a bunch, runoff from agriculture, so the pesticides, the fertilizers, whatever it may be, that can run off as well. But the problem with groundwater contamination is it's extremely difficult to clean, and it also takes a very, very long time to replenish. So it's going to take a long time to dilute whatever that contaminant is. And then with the groundwater, a lot of the times this is used for drinking water. So if we do wind up with a contaminant in there, it could essentially just kind of ruin that entire supply of water. Okay. And then with the oceans, so up to this point, we were kind of mostly focused, or thinking from the lens of drinking water and water that humans are going to use. But in addition to that, there's also the oceans, which are highly, highly polluted. A lot of the stuff we've talked about, so pesticides, manufactured chemicals, so that could be like the PFAS, oil spills we haven't talked about, but those I'm sure you've seen in the news, where you just wind up with the oil slick covering large amounts of water. And those, especially with the deep water drilling, has the potential to release like an insane amount of oil if there ever is a spill, similar to I forget where the one was in, I think it was in the Gulf of Mexico. And then again, the microplastics going to be a huge problem with the oceans. But there's also the put it in there. But there's also the essentially kind of just like two islands of trash just floating out in the Pacific. Just because the oceans have kind of just served as a giant receptacle almost for just all of the different trash that people don't want. But like we said, when we're trying to think about keeping water clean or cleaning it after it's dirty, the cheapest way to do it is just by preventing the pollution in the first place. But if water does become polluted, it is possible to clean it up. So the Rhine River in Europe, very important in terms of shipping things from different ports to port to port, became highly polluted. But in the recent years has become much cleaner. And then one of the most famous examples is Minamata Bay. So this became polluted with mercury just from dumping from industrial sources. And then in this region, seafood was sort of the staple diet. So people were consuming large amounts of seafood. They were then consuming large amounts of mercury. And ultimately, people got very sick from it. And they were no longer able to eat that seafood. But over time, they were able to stop the dumping. They were able to clean up the water. That mercury became diluted, so it went down to a more reasonable concentration. And they wound up seeing the ability to consume that seafood return. So just like with the air quality, it is possible to restore it after it's kind of been polluted. But it's a more difficult process. It's a more expensive process. It's already going to have negatively impacted probably many lives at that point. So it's always a better option to prevent the pollution beforehand rather than kind of trying to be reactive and dealing with it afterwards. And then with the treatment of water, if we're looking at wastewater, it's going to be a little bit different than if we're looking at drinking water. But we talked about it before. You can ultimately take that wastewater and get it to a point where it's clean enough that it could be used for not drinking water necessarily, but could be used for other purposes. So we're recycling that water, just like when we're recycling any resource. Always going to be a helpful sort of process. So in this case, when we're looking at wastewater, the first step, the primary step, is kind of just to remove those large pieces, whatever that suspended material may be. That's what we're showing in these couple of steps. The second step, they introduce bacteria that's going to consume the organic matter. And then the final step, or one of the final steps, is some sort of disinfection process. And there's a couple different ways they can do that. Sometimes they use UV light. That energy of the light is able to kill those different bacteria and microorganisms, whatever it may be. Or they can use chlorine. There are a few other options as well, but those are probably the two biggest. And then just as it's going through this process left to right, we're just seeing the quality of that wastewater get cleaner and cleaner till ultimately it gets to a point where it's been purified enough that it can be used for some other purpose. And in addition to kind of having a formal sort of wastewater treatment setup, what some places have done is a constructed wetland that ultimately does the same thing, just in a slightly different manner. So they actually kind of create a wetland. They have these different plants and different setup, and the water just comes through. And like we talked about, wetlands have the ability to purify water. That's just what we're seeing here. This does take a pretty decent amount of space, though. So what one, I forget where it was. I think it was Wisconsin. Could be totally wrong about that. But what one location did was they kind of modified this idea. And instead of actually having kind of like a true wetland, What they did was they just made a bunch of little tanks that kind of served as sort of isolated sort of sections of this wetland. And they were able to reproduce the same thing. So it kind of just shows that if a company or a business wanted to enact a system similar to this, it would probably be somewhat expensive, at least initially for sure. And it would still require at least a little bit of land. But it would be a possible sort of process to undertake. And you can see how successful it is in terms of actually cleaning that water. And these numbers are related to the sort of the smaller system that business set up rather than the more traditional constructed wetland. But it decreased the biochemical oxygen demand almost completely, removed almost all of those suspended solids, and then helped remove almost all of the nitrogen and the majority of the phosphorus as well. So it really helped improve the quality of that water. Actually got to the point where the water that they were expelling was cleaner than the water that they actually received initially. And that's where we're kind of end it for this chapter. So the last section of the chapter just focuses on the Clean Air, or the Clean Air Act, not the Clean Water Act, excuse me. I've been talking about water the whole time. So I'm going to leave that section up to you just to read it on your own. But if you have any questions, let me know. We can discuss that one at any point.